Okay, so we talk about RSA and we showed how the security relies on the hardness or interactability of the factorization problem. So now the question is, how hard is the factorization problem? So we talk about the trivial division at the beginning of these lectures, and we showed that this is an exponential time algorithm. That is, if you want to factorize a number n, checking every prime number less than square root of n and check if it divides this number n, this is trial and error method. It is an exponential time algorithm. So question is, can I do something better? And the answer is yes. So let me first explain Pollard's law algorithm, and then I will explain how you can use it for factorization. So given a finite set S, you have a map F from S to S. You choose a starting point x0 in this set. So let's say that there are elements. Then the next element is just fxi, okay? So xi plus 1 is fxi. And we are trying to find a collision where xi equals to xj, okay? So in general sense, you can think about trying two inputs that is going to give you the same output, right? So you can use this for searching hash function collisions. One way to find a collision is store all of the xi's. So since you are calculating new xi all the time, you can simply check if this new value is observed in the previous ones, right? So this way you can find if an xi equals to xj. So another way is to, do a baby step, giant step optimization, because if you do this, you have to store every value, right? This is not memory easy algorithm, because if you are going to calculate a lot of xi's, then it will take a lot of memory. So in order to reduce this, we can do some kind of a time memory trade-off. If you only check whether xi equals to x2i, at each iteration, we will eventually find a collision. Of course, if this algorithm has a collision, if not, you won't find anything. But since you are mapping the same set to itself, at some point you are expecting to find a collision. So this algorithm has complexity square root of r. R is the number of elements in this set. Okay. So you can use this for factorization, or you can use it for many other type of algorithms. Okay. So let me show you how you can turn this Pollard algorithm into factorization algorithm. So assume P is a non-trivial factor of n. Okay. Choose an easily evaluated map F from Zn to Zn. Okay. For example, fx equals to x squared plus 1. A very simple mapping, right? Choose a starting point x0 in this set. Here a collision will mean xi equals to xj modulo p, right? This means p has to divide xi minus xj. But we also have p divides n, because we assume that p is a non-trivial factor of n. So p has to divide greatest common divisor of xi minus xj and n. So actually p has to be equal to this greatest common divisor, but we'll see. So what you do is compute xi, x2i for each i, and check whether greatest common divisor of x2i minus xi and n is different than 1 or n. Okay. So it might look counterintuitive, but as you can see, here our aim is to find this, but I cannot calculate this because I don't know p, right? My aim is to find p. But if there's such a collision, this would mean this. So our aim is just to check. So you constantly calculate these two values and check the greatest common divisor with n. So since this had a running time of square root of r, in our case, this set has n elements. So this algorithm requires square root of n steps. Okay. So if n equals to p times q, where p and q are two primes of the same size, then Pollard's algorithm can find the non-trivial factor of n in O square root, actually fourth root of n steps. Okay. This is mainly because p is kind of has a size that is close to square root of n. This extra 2 comes from there. This is why in RSA only 2 primes are used and they're close to each other. Okay. If you choose one of them really small, then Pollard's rule algorithm will give you a very fast answer. Okay. So do we have something better? So this is, still an exponential time algorithm. So actually we have sub-exponential time algorithms to solve the factorization problem, like Dixon's method, Billard-Morrison algorithm. And the first one uses random squares, the second one uses continued fraction expansion. Third algorithm, we have quadratic C method. And finally, we have number field C method, which is the fastest compared to others. So for this reason, we have to use really big primes. This is why in elliptic curves, choosing a secret key of size 256 bit is enough because it gives you 128-bit security. But in RSA, due to these sub-exponential time algorithms, in order to have 128-bit security, you need 3072 bits of secret keys, right? The value n here, actually. Your actual group modulus, not the secret key, sorry.